Question 1 is giving us an equation here and wants us to use what's called implicit differentiation to find dy dx, which means find the derivative. So implicit differentiation is a process that you're going to want to use whenever you start seeing sort of x's and y's showing up mixing together in an equation. Everything up to this point when you were asked to find a derivative always started off as a nice y equals with some x's over on the other side. This is starting to be a different setup than that. As you can see, the x's and the y's are all together on one side, but we still need to do what we did on the first type of problem, which is find the derivative, find dy dx. So to do implicit differentiation, what that process looks like is I take the equation that they give me and I wrap it in a set of parentheses, and then I'm going to dx that equation. So I'm going to take the derivative of each one of these pieces with respect to x is what that means. And so my little saying that I use whenever I'm doing implicit differentiation is every time I take a derivative, I get extra shit. And so what that extra shit is going to look like is envision there being this little box behind that d up on top right there. And every time that I take the derivative, I'm going to get d, and I'll fill that box in which whatever the letter is I took the derivative of. So I know that sounds complicated, but it's really not. So we start here with 3x cubed. You take the derivative like you normally would. You do your power rule. So you bring your 3 down. 3 times 3 gives me 9x, and then subtracting 1 from the power gets me an x squared. And so here's where I'm going to get my extra shit. I took a derivative of an x, so I'm really filling that little box in with an x. So it'll be dx over dx. So then I'd be done with that first derivative, and I get minus, and go and take the derivative of y squared. Again, take the derivative as you normally would, so you'd bring that 2 down in front, you get 2y, and then subtracting 1 from the power would get you y to the first. Because we took the derivative, we get some extra shit, and this time, because we took the derivative of a y, we fill that box in with a dy dx. And then from there, the derivative of a constant, the derivative of a number, no matter what method we're using, is always 0. So from here, it's now just an algebra problem. We're trying to solve to get dy dx by itself. The first thing that I always do is what I call a cleanup step. As I come through here, I have the 9x squared, but then the dx over dx cancels itself out. It's like having 5 divided by 5. Those would cancel out and leave you with just a 1. So I don't need those dx's. I get minus 2y, and then I have my dy dx equals 0. Again, this is just algebra. Treat dy dx like any other variable and get it alone on one side of the equals. So the first thing I would do is any addition and subtraction. So I'm going to subtract over this full 9x squared term to the other side. Those will cancel out. That'll leave me with negative 2y times dy dx equals negative 9x squared. Trying to get dy dx by itself, this negative 2y is being multiplied by that dy dx. So to get rid of that negative 2y, I need to undo that multiplication. I'm going to divide both sides by negative 2y. So on the left side, those negative 2y's are canceling out, and I'm left with dy dx equals negative 9x squared over negative 2y. And as we look to our answer, the key here is to know that this negative negative, a negative divided by a negative, is always a positive. So really our answer is positive 9x squared over 2y. So the answer to question 1 would have been answer B in this situation. So implicit differentiation is just this little game of every time you take a derivative, you're going to get this extra stuff out.